Questions about the first part of class? Comments? Is your bracket any better yet? No. All right. Well, let's see some model fit then. So here is the model fit from the analysis. Sorry, the numbers are small, but let me try to blow them up real quick here. If you haven't run Levon in a while, this probably brings up bad memories. That's okay. But here, take a look. This, what was this? Sorry, let me just say this term under the box, the robust, is what we're looking at. We use robust maximum likelihood. This box, or this little area at the top, is the likelihood ratio test between our model, right, the one-factor model, bless you, and the saturated model. So the degrees of freedom up here are the difference in the number of parameters between our two models. And sure enough, 252 is what we had calculated, thank you, Hong Ling, is the difference between 300 and 48. Right? So that is our difference there. That's saying, okay, so you have the saturated model has 300 parameters. I guess you could look at it another way, pardon me. To be more explicit, because this was a question from before, and I really want to say it's really the difference between 300 and 24, that's the total number of parameters, and 72. Right? That's really the difference. But because of the mean side, 24 and 24, all means are accounted for essentially. We just sometimes omit them from our thought. We should really be adding them up all together. So 324 minus 72, the difference in those parameters is 252. So our null hypothesis is that the saturated model, or sorry, our model fits as well as the saturated model. Our alternative hypothesis is that's not true. No, it doesn't. Our test statistic is 2,697.490. So here's the thing about things that are chi-square, right? Just a rough idea. A chi-square, the distribution of a chi-square is this odd, skewed-looking thing. The mean of a chi-square, which is kind of, you know it's not going to be the tail. The mean of it should be equal to the number of parameters, number of degrees of freedom. So a good footing, if you want a rule of thumb for how to interpret chi-squares and degrees of freedom, like you should have a chi-square right around the number of degrees of freedom. That gives you a good sense that the model will fit. And take a look at how big our chi-square is compared to the degrees of freedom. We're a factor of 10 bigger, factor of 11 bigger, right? That's huge. So this is telling us one factor. We do not have a one-factor model here. We don't have a gambling factor here. That's what this test is. But as you know, this likelihood ratio test, conveniently in the world of SEM, we just discard it. Anywhere else in statistics, that's important, but in SEM, forget it. It's really too strict. I mean, who really needs good model fit anyway, right? The uniformly most powerful test, forget it. Let's talk about how far off we are. That's where all the other indices are. The CFI and TLI, we want, remember, the rubric or the mnemonic device to remember what we want these to be. We want these to be high, close to 1. 1 is roughly perfect, although they can go above 1. Good fit is something like 0.95 and above. These are 0.68 and 0.65. Not good. So that's another 0.2 of our evidence is not saying it's fit. The RMSEA, we want this thing to be less than 0.05. And again, it's a root, so we want it to be low. Lower is better. An index is high, like the stock market, the Dow Jones index. So 0.086. Believe it or not, I've seen people publish on 0.086 before. Have you? Have you seen any journal articles with scales in? Did you see RMSEA? 0.086. I've seen people go, that's pretty good. Yeah, this is pretty good. But because this is class, and I want to teach you the best way of doing it, which doesn't mean the way that we usually do it, but the best way of doing it, I would like to say that's too high. We just want it to be lower. And the standardized root mean squared residual, or SRMR, 0.087 is that value. So that term, that people have said 0.08 or less, but I don't know. That to me is like if all you had to rely on was the standardized root mean squared residual, you don't have good fit anyway. So does all this make sense? Does this all ring a bell? So if you were sitting here, imagine I'm your student, and you're on this is my PhD. I'm trying to build a gambling scale or do gambling research. And you're on my committee. And I'm like, hey, here are the results. What do you tell me? not that, you know, it's not one of those cases where, you know, I've got a job waiting for me and I need to graduate tomorrow. Or, you know, the type of, okay, we'll turn a blind eye to some things. Go ahead, here's your PhD. If we have, like, nothing but time and I'm, like, you know, locked in here, what do you tell me? Start over. Choose a different field. Maybe this isn't, maybe you're not cut out for this. Start over on the analysis. That's a good point. So you don't agree with the fit. You don't think this fits, right? Anybody else? No. Now, again, you will see people publish papers with the root mean square error of approximation, RMSEA, at 0.086. But if you look at the totality of the evidence here, you know, our terrible likelihood ratio test, very small values here. Sorry, this is terrible. This is terrible. This is terrible. All we have going for us is this root mean square error of approximation. I don't know. That's just not a lot of evidence to suggest this model fits. So I'm going to keep moving forward. So, hey, we just covered this slide. Actually, here we go. Model fit is not good. We should not interpret the model estimate. So we're not even going to get down to these estimates right here because they're not valid yet. We're just going to try to make the model work better. It's our job to figure out why the model doesn't fit good. Right? And I'll note, we spend, I would say, the bulk of our time trying to achieve really good model fit. All right? It can take what seems like forever sometimes. All right? You should see, you should have seen me circa 2002 with my friend Bob in grad school with this stuff, because this process with these data it was months and months. Oh my gosh, it's never going to end. But we finally got something, I think, that was good enough for somebody. But even if model fit is good, you go through all that process to get model fit working well, your results may not mean much, because you could have good fit and still not measure things. I've seen it, I've heard it. Actually, Lisa tells a story. She's been on committees. When she was at Nebraska, she was on a number of students' committees that dealt with a measure of executive functioning. I don't know what this is about. I think I've heard about it in older adults where it's more like, can you do the basic things you need to do to, you know, get up in the morning, brush your teeth, you know, tell time. Things that are cobbled together that talk about, hey, can you live on your own, let's say. And she found really good model fit, but all the factor loadings were essentially equal to 0, right? So that meant every item had a 0 loading, which really meant there was no scale to be had, right? Executive functioning didn't seem to matter on each of these items, right? Really, the items were uncorrelated, right? So you can get good model fit and have not a good result, but model fit is your key to talking about the results itself. So just remember that as you go forward. This is often lost when you submit a paper. Frequently this is lost. It is, I've seen it happen a number of times, particularly with mediation analyses. You know, the 3 variables with that triangle looking thing. That model fit is perfect, right? It's a saturated model. You can submit a paper, you can say that, and I would almost be willing to wager a bet 3 out of 10 times you'll get a review back that says, where's the model fit? I'm not going to publish it, there's no model fit. The model fit's perfect. You know? So people don't understand the idea that model fit is everything. It's not everything. The flip of that is, I've got great model fit, let's publish the paper, and then you look at the results in a published paper and the results are garbage. So remember, model fit's just a chance to look at the results. But to make a good story, to make it really make sense, you need to have model fit and you need to have the results. Frustrating, right? Yeah. What is that you said, Jennifer? You need to start over? And I took it to mean maybe this career isn't for you. That's what I think sometimes when I'm trying to help someone get their model to fit. Next week's class, by the way, I took data from somebody whom you were working with, actually. She asked, could you help me try to get this to work? And we did everything by the book, and it still wouldn't fit. And then we started looking at the data. We added a few other things that we should have added to control for some of the ways that questions were asked, and dang it, it was the best fit I've ever seen off like that. I'm like, whoa, it does happen. Once in a while it happens, you can get good fit with the survey, but it took a while. Okay, so let's take a look at where misfit happens. Actually, let me stop. Do you have any questions for me? Is this going at a good pace? Am I going too fast, too slow? I just want to kind of just not dive in and overwhelm you like I did with some of the slides in the beginning of class. Build up to a crescendo again. But actually, I prefer not to overwhelm you ever. I know I put too much into the class at some points. So. Anyway, let's now, since the model isn't fit, and we all sort of agreed on that, let's take a look at what we can do to make the fit better. One of the things we cannot do is look at any model-based parameters, because our model-based parameters are biased. Right? So we can't just go to our factor loadings and say, well, I'm going to take out all the items with low factor loadings, because the low factor loadings may just be a consequence of the 48 parameters we had trying to do the work of the 300. Right? That could have just been the slaughter at Sparta, or where was it? No, it was before. It was that pass before you get to Sparta. Anyway, that could have just been it. So we didn't want to do that. So we can't use those. We can't use modification indices because, if we're doing just one factor, what are we going to modify? Right? All the parameters in a one-factor model that could be added have been added, with the exception of residual covariances. But we're not going to open that door yet. Right? We could add a residual covariance or a error covariance between items and make fit better, but we do so at a consequence of definition of the factor. So we're going to build a factor that we know what it means, and so we're not going to do that. So what we really have to do is take a look at the residual covariance matrix, right? Which is the difference between the saturated model's 300 parameter covariance matrix and our model implied covariance matrix, using that matrix formula on the board there. Thank you, Megan. All right. So we have these two covariance matrices. We want to see the discrepancy between the two. The places where they're most different is the place where our model fit needs to be improved the most. Right? That tells us the most misfit. Our model is really not accounting for this correlation or this covariance between items well. So what I like to use are the normalized residual covariances. Right? Those are the difference. So you take saturated model covariance matrix and you subtract from it your model's covariance matrix, so you have a difference. But then you divide that difference by essentially the standard error of the difference between the two to get a result that's like a z-score. So what we're going to have is a matrix of z-scores. If a z-score is really big, we're going to say there's misfit between these two pairs of this pair of items. And if a z-score is close to 0, we'll say, oh, this fits pretty well. But using that standard error in both of those allows us to compare and contrast. And the reason we need to do that is that each of the items may be on a different metric. It may have a different, and will have a different variance estimate. And so just looking at the raw difference between the two doesn't give us an instance to understand a magnitude, right? We may have an item that has a variance of 100,000 and an item that has a variance of 1. The variance of 100,000 has a lot bigger range to have a difference in, right? If you were off by 10,000 on it, it's not as bad as if you were off by 10,000 with a variance of 1. Right? So that's why we want this normalized residual covariance matrix. Okay, so they like z-scores, normalized residual covariances. You can get that. So we're going to go looking for values bigger than plus or minus 2. Bigger than 2, less than minus 2. Remember that z-score thing, 1.96, negative 1.96. It's the 95% range. You can pick any cutoff you want to do. I'm just looking for a rubric to statistically look for where misfit happens. And this is just helping us flag, hey, there might be a problem here. If you have a residual that's positive, right, that indicates that items are more related than your model expects or predicts them to be. Right? So something other than that factor is creating that relationship. Right? If the model was right, gambling would be able to describe this relationship between this gambling factor would be the thing describing the relationship between these two items, and only it. But if we're too low on describing it, it's like gambling and other things are telling us happening. Negative residuals are a little bit weirder. Items are less related than our model predicts them to be. And that's discrepancy that happens when you look at a model and your results get pulled off because they're it's biased because of misfit. So you've got this negative residual. It's happening more or less because of the leveraging of 300 terms onto 48, essentially. It's harder to describe. I'm kind of stumbling on my words for it, but either way, it's bad. Either way, we're having misfit. So we can find where the model isn't fitting well, but what this isn't telling us very well is how to fix the problem. Right. So here, look at that. If you type the word residuals and you give it into Levon and then you give it the word model, the name of your output, type equals normalized, you get this big covariance matrix looking thing. The terms in this, the numbers in it, are the normalized residual covariance. I've taken some syntax and I sorted these, and I'll do that on the next slide, but let me just talk about this here. Note the zeros on the diagonal. All right? That is not a mistake. That is actual correct. Our diagonal, what does a diagonal on a covariance represent? The variance, right? So this is saying how far off are we on the variance of each item? We're off 0. We fit those perfectly. We fit those perfectly because we have this parameter, this for each item, the residual variance. It essentially soaks up the gap between what comes from the factor and what's left over on the item. So we never really have to worry about the variances of the items if we're doing this fully parameterized, where we have each item having a residual variance of its own. So that's pretty cool. We just have to look at the covariances then. And so now you can see each of these covariances. Let's take a look at item 1. GRI1 is item 1. Each of these numbers in this column are the normalized residual between item 1 and each of the other items itself. Of the scale itself. So here, 2.718. Hey, isn't that E? Help me out here. No. Anyway, sorry, coincidence. What's Euler's constant? E to, isn't that 2.7181? Anyway, never mind. That number is actually the residual covariance. It's not just E. That tells us that our model is under predicting that covariance. It gives us an under specification. So really, gambling is not enough to describe the difference between these items. It's one factor of gambling. Right? If we go through and look at all the values on here, you'll see that, for instance, the biggest absolute value term is on GRI 19, 3.729. And the smallest one, we get some that are close to 0, which are good. We have a negative 2.464 over here. So it's telling us if we wanted to go and figure out what was up with this, we would take a look at each item 1 and each of the other pairs, each of the other items with it. And we might see, for instance, one of the things we might see is that, hey, maybe these are talking about gambling under a very specific context. Maybe gambling last week. Maybe there is a last week factor we need to account for. So one of the ways of fixing this is adding another factor. But in today's class, we're just building a one-factor scale because that's the kind of the building block of everything that we do. Adding another factor we can't really use. Here, take a look at some of the bigger values here. Look at this, GRI 20 with GRI 4. There's a 14. We're way off on that one. GRI 12 with GRI 20. Way off on that one. Right. GRI 20 and 22. Way off on that one. Some of these you're actually going to have a real good reason for in just a bit. But I then took those normalized residuals and I made it so that they were ordered. And this is not the right number. Anyway, this is a listing, but these are clearly not the numbers that we just saw because some of them are smaller. No. We can go and let's pretend they are. Gosh. You can get the numbers from the analysis. This was in my early days of working with Levon. This is one of the mistakes I had made. So my apologies to you. But let's say that these are it. These are the bigger values of normalized residuals that you see. These are their values. And here are some of those items that we looked at. Here's item 20. When gambling, I have an amount of money in mind that I'm willing to lose, and I stop when I reach that point. This is item 20. This is supposed to measure criterion 6. The R here says that this is actually a reverse-coded item. Have you include reverse-coded items in your surveys? Yeah. Okay. So somebody who rates this highly is less likely to be a gambler than somebody who rates it lowly. That's what the reverse coding happens. Item 22, gambling has hurt my financial situation. That was supposed to measure criterion 10, not reverse coded. Item 4, I enjoy talking with my family and friends about my past gambling experiences. That is reverse coded. We would say that I think the criterion for this is tries to hide their gambling activities. So somebody who rates this highly would say is probably not a gambler. So here, just as a self-assessment, I'm bragging about me learning how to gamble with grant money. I'm totally not a gambler. Right? I can stop. It's okay. And then item 12, when I lose money gambling, it is a long time before I gamble again. Again, reverse coded. I think criterion 6 is the criterion that talks about when you lose money gambling, you frequently return to try to win it back. Right? You notice anything of these 4 items that stand out that they have in common? Although item 22 maybe not as much. Actually, certainly not as much. 3 of these 4 are reverse-coded items. Right? And that's actually one thing you see a lot with reverse-coded items. The idea of reverse coding induces something in addition to the factor on the item itself that causes scores to be a little bit different. Now, it could be people are not paying attention and just rating as they would. But it could also be something cognitive, right? Is it, when we reverse code an item, we usually take its score, if these are scored 1 through 6, and we flip it. We take 7 minus that original number, and now it's this reverse coded score thing. That's a really specific process. Cognitively, perception may not work that way. Negating something you may not negate as strongly as you endorse, right? And that is a phenomenon that almost happens always with reverse-coded items. The fix for that, by the way, in a more than one factor model we'll show next week. Something we call a methods factor, where we actually build a factor for reverse coding, and we have it load onto items that are reverse coded. And that factor is essentially the difference between, it soaks up these differences that you see in this residual covariance matrix here. It helps with it. So yeah, that's one of the problems. Right? So we could think about it. Another thing that you see here, when we look at our items, is that sometimes we see finances, we see money, we see financial situation. Sometimes if you ask items a lot that they have the same word in them over and over and over again, people again, it's a perception thing. What money means to me and what finances mean to me may be different than you. So if you put the word money in, and maybe I'm really prone to worry about money or something along those lines, that might be the cause. We might have a method factor with the word that we're using itself. It's an odd mix of things that we have. So, but what we can do to fix this is one way, which is where we can add parameters. We just mentioned that. Method factors. Right, these are additional dimensions. Reverse-coded items, keywords. Megan, you gave us this. We were working on a project with the
when I'm upset scale.
The when you're upset scale. What was the scale originally called? EATD. It was something about. Yeah. What was it called? Eating attitudes disorders. Yeah. See, I've got body dysmorphic. I've got eating. I kind of grift along for data these days. So. Anybody have data I can borrow? And what did you see when you looked at the items?
Different body parts.
They had different body parts explicitly said in some of the items.
Yeah.
You had like a body part factor, right?
So it would be like gender differences.
Yeah, gender differences that you might see. There were also, you said attitude. Mm-hmm. What was it? Something about, there was some keyword about some emotion that you might experience that was over and over and over again. So anyway, you can see this, and it happens in a lot of constructs. If you look at their items, and this is one of the questions I had given you in homework this week, homework 1, question 1. You have the items. I want you to look at the items. Start to see it. This is a scale, I think it was published in 1983 on body dysmorphic. Actually, no, this scale is not 1983. There's another one. Getting my scales mixed up. Yours was, I think, in the 80s. Anyway, this scale is out there, and you look at the items because sometimes you'll see these effects. You'll see weird worded items. You'll see common things that show up over and over and over again. It gets back to the idea that we don't have factors, all we have are items. And if our items are somehow systematically biased to make people respond in certain ways, where our results are going to suffer from it. Right? But it happens way often. It happens more often than you think. It's really hard to write really good items. So I'm not trying to criticize those who wrote the items. It's just when you start to look at surveys, start with the items. Even though this class is all about the quantitative methods that go beyond it, really item analysis starts with reading them and trying to think about them in a bigger picture. So we could add additional factors, but we're not going to do that this week because I'm trying to build one factor by itself. When we have more than one factor, this scale now represents more than one thing. I just want to have a pure, nice, happy gambling scale. Now I'm sounding like Bob Ross. A happy little tree. Question? No. Happy little gambling scale. The other thing we could do is add residual covariance between items. Do you remember homework 3? How could you forget, right? I'm getting scowls, frowns. Between one of the things that one of the catches in homework 3 was the idea of residual covariances in the model between certain endogenous variables. Right? You had to build up, and if you just went straight from, if you went straight from models 1 and 2 into model 3, it didn't give you all the right ones in the model. You had to go and figure out which residual covariances needed to be there. Those residual covariances talk about additional correlation between these endogenous variables. It talks about how the residuals, or how once we've predicted a person's score on these, might covary together. And they're model parameters. They just show up in the model. They take care of it if it needs to be there. We could do that in a factor analysis. We can go and add a residual covariance between a pair of items. And believe it or not, the model fit will get better. But it's something I'll call a dangerous solution. Because when you add a residual covariance, you are essentially saying that you cannot explain why this pair of items have extra correlation. And in the factor analysis, the factor should be explaining the extra correlation. It should be explaining the correlation in its entirety. So you'll see people in published papers put in residual covariances into their factor analysis. And really what that's doing is saying, if I could do that in our scale right here, but I couldn't honestly do that and call this a gambling scale. Right? It would be, oh yeah, that's gambling and some other things. That's really what I should call it. Gambling and stuff. You like that? The gambling and stuff scale. Because that's really what it is. That residual covariance should be described by the factor. You shouldn't have residual covariance if your factor is truly what the scale happens to be. So the fact that you had to put a residual covariance means that's the stuff part. Unexplained, it just happens to be there. And to me, when I see that on a paper, it's somebody saying, "Oh, I can get around model fit by adding these terms. Oh, I can just add residual covariances and we're good." Not cool. So, yeah, Megan.
But if it's a method effect, can you explain it in the paper?
You can explain it in a paper if you have a method effect, but you can also put a factor on it with the method effect. And so the residual covariance and a factor, if you have, let's say, imagine you have, here we had 3 reverse coded items. Those 3 items, because we have 3 of them, we could define a factor all by themselves with it. We could have also gotten away with a similar identical solution, identical model, by putting the 3 residual covariances between them. So model 1 versus model, essentially now we're in competing models territory.
Would you have a covariance between the factors?
In the methods factors, no. So you have to have 3 variables to do it. So essentially, if you have, let's imagine this scale, we have 2 reverse coded items. We couldn't put a method factor on 2 reverse coded items by itself. We need to have a third, or we need the correlation of the method factor with the thing. We don't usually correlate those two. So we could include a residual covariance if we had 2 items that we needed to go and add it to it. But yeah, and you could explain, oh, that's a method effect or something else. But more often than not, when I see, or actually, let me not go into it. For this survey, I can't see a reason of adding it because all these items are measuring gambling, and if I add residual covariances, say between the pair of these items, it's gambling and something else that's there that I don't know what it is. Right? So you can, there's a journal that maybe you've heard of, the Journal of Psychological Assessment, or psychological, I think it's just called Psychological Assessment. It's an APA journal, and pretty much I swear it comes out every week. It's published very frequently, but it's published reports of doing quantitative analyses of scales. Usually things that are new, inventories and so forth. So this type of work that we're doing here would be something you would show up in that. Okay, gambling measured, 1-factor scale of gambling called something or other. And you'd see this report of, we took these items, we took this sample, here's the methods that we did to validate, or to show that the model fit, ta-da. Right? That's all we're doing with it. If we added residual covariance into it, that seems really hokey to me. Right? What we're after is gambling, a scale that measures gambling. And when we add the residual covariances, it's possible it's gambling and other things.
Like finances?
Yeah, gambling and finances, or gambling and people's tendency to, or reverse codedness, or something along those lines, right? That's it. Your EATD, I think 1-factor had 6 out of 7 items that were reverse coded. So along those lines. So yeah. Anyway, questions, thoughts. So the big picture about it, it's not necessarily cheating. I just say it's dangerous, right? If you see it, put a flag up in your head. Say, okay, residual covariance here. Why? It may be justified. But in the times I've seen it, it's usually kind of the way to say, hey, look, the model fits. Good job. Call it good. But now we've got a model. You know, the best fitting model is the saturated model. That's all full of residual covariances, right? They're all residual at that point. We don't use it and say, hey, we have a 24-item scale of gambling, and look, no factors, but just residual covariances, right? So we have to have a blend of all. You see what I'm saying? Anybody? Yeah, maybe? No, yeah. Anyway, okay, so solution number 1, we're actually going to do that next week. And next week's class is going to be a new lecture, which is really dangerous. I code it in between diaper changes. Try to type it up. But no, it has this awesome result that one of our DLM postdocs got me to work with. And I'm going to show it to you for it. Demonstrating methods, factors, and so forth. So we're not going to add a factor now, but that is one way of doing so when we go forward. I do like to think when you build a scale with more than 1 factor, though, I like to make it so that it's like you do a series of 1-factor analyses first. And then you put them together because you cut down on the places where model misfit might occur. Like if we had started here, like this instrument we're using here actually tried to measure 10 altogether. And we did our analysis starting out with all 10 all at once. And it really crashed and burned. It was terrible. Where does it misfit? Well, you got to go to each of the factors by themselves now and take a look. And so it makes the solution to the analysis a lot more simple when you start with one factor at a time. Solution number 2, we could look at the residual covariances. Here's the modification indices of those residual covariances. And you see how big they are. And again, these are some of the items that are reverse coded. So that's not cool. Here's a slide. I believe this is from one of the Brown chapters you looked at. Residual covariances actually represent multidimensionality. Here you have a general social anxiety scale measured by 6 things, but perhaps there was a residual covariance between 2 of those items. That's almost like saying that perhaps those items were measuring public speaking anxiety by themselves. So it is more straightforward to go and put a factor there than a residual covariance. A residual covariance, remember, is an acknowledgement that the model didn't fit here, so I'm just going to put a parameter there and not know why it's there. Okay. Getting into ways of fixing the model, part 2, we can reduce the number of items, reduce the number of factors. Actually, if we had more than one factor, this would be one of the cases. But what we can do for us, we're going to drop items. I say here drop items with non-significant loadings. This is actually encountered what I just said. I don't like this one yet because the loadings are all, or any of these really, these are model parameters that are going to be biased. So I'm going to just kind of line those out right now. I'm sorry. As I've taught this, I've become more in tune with what methodology should look like. So I'm just going to line that out right there. All right. So dropping items is the thing that we're going to do. This happens all the time. When you look at the GRE is comprised of test items. You took those. Those are the items that were left over. Did any of you have to take an extra section in the GRE? Is that how they did it? All right, that extra section wasn't scored for you, but you were giving them pilot data or field test data for them to make items out of later on. The items that they took from that didn't fit using their standard of comparison, their version of RMSEA, were dropped. Done. Poof. Gone. Not like it never even happened. Right? They could have represented another dimension. It could have been math. It could have been parts of math, like algebra or college algebra or geometry or something along those lines. We don't know. They dropped them. Right? But we're going to do that here. It's an easy way to make the model fit. But here's the thing when you drop items. Every item you drop was written for a reason. In our gambling scale, we only had 24 to begin with. There were 3 factors that only were measured by 1 item apiece. If we drop that item, that criteria, or that criterion that was measured with that item, no longer is represented in our gambling factor. When we talk about what the factor means, essentially, like in a sense from validity, and I'm not a person that preaches validity a lot, but just what that factor represents now cannot be that criterion that we had dropped. Right? So the nature of the construct is changing when we're dropping items. It's no longer gambling. We're still going to call it gambling, but it's no longer the gambling that we thought we were constructing when we built all 24 items for the first place. Right? And the same thing with the GRE, the same thing with large-scale testing, and also, if you're dropping a bunch of items from different content areas, you're changing the scope of it. Now, in the GRE's case, the content area is mathematics. So it has a little bit more detailed blueprint than that. It doesn't start with 24 items. They start with thousands of items, so that if they end up retaining hundreds of them, they still have the same specs of the test that they think they have. But for this, it's really going to change the factor considerably if we start dropping items. Now, one thing we cannot do when we drop items is make likelihood ratio tests or any other type of model comparisons that involve likelihood ratios, because the likelihood comes from that multivariate normal that has all the items in it. We have 24 to begin with. Remember the DM norm homework? Nightmares from before. I'm surprised you still came back. Thank you for coming back. But if you calculate a multivariate normal for everybody with 24 items, and you want to, let's say we drop 12 of them, which is what we're going to end up doing, right? That multivariate normal is on a different scale. We can't compare them. 24 versus 12. So we cannot do any direct model comparisons at all. when we change the number of items. Model comparisons assume the same number of people taking the same number of items. When we change either of those, it doesn't work. Okay? So what we can do, though, is we drop the number of items and we just see if that new model fits. We don't compare it to the old model because there's no comparison to it. We just see if the new model fits. Questions? Okay, cool. So how do we drop items? Well, not being a gambling researcher and only hearing about the DSM, although I do have a copy in my office. Version 4, not even the text revision, just really version 4. I'm going to look at quantitative evidence for Misfit and drop those items. If you were doing this from a better perspective, if you knew the construct, if you were studying it and knowing it, you might go and say, oh, I don't like how I worded this item, or know which item is better. So this is really kind of flying blind at it. But just to demonstrate the process, I'm going to do that. If you're doing this, please put more thought into it than the numbers. The numbers can be misleading. Okay? But what I did, I took that big triangular matrix of all 24 items, and I counted up the number of times an item had significant normalized residual covariances. So I went down each column and I counted up the number of times I saw a value that was bigger than 2 or less than negative 2. And lo and behold, item 22 had 16 values, right? There were 24 items on the test. That means item 22 did not have good fit with all but 8 of them, right? It didn't fit well with 16, it fit okay with 8. So I'm like, that's a candidate to get that item out of here. It seems like it's doing really badly. Item 22, item 4, all these, all right? There's our list. There are 9 items with 10 or more normalized residual covariances. I just picked this out of a hat. 10 or more, whatever. It just looked like a number to use. And this is what happened in your homework this week. I have this specific thing. I say use all items, now drop these. So if you go and look at the residual covariances from the all items version of it, you'll see the ones you're dropping are the biggest over here too. Right? The scale will be different. 10 or more, I have 24 items on the test, on the survey. So having 10 or more is different. On your homework, I think the survey has 13 items, maybe 12. Right? Getting 10 or more is unlikely because you don't have that many items to misfit with. It'll be more like 6 or 7. So, anyway, it's very arbitrary. It's just trying to find a way to remove it. When I remove an item, what happens to our saturated model in terms of the number of parameters? We lose one mean. Let's imagine we have 24 items. We go down to 23. Right? We lose one mean. We lose one variance. And we lose 23 covariances. So by taking out one item from that, we go from 300 parameters down to 275. So the ratio of model parameters, which would no longer be 48, I think it would be, I'm sorry, 72. It would no longer be 72. It would be, we drop 1, 2, 3. We think we'd 69 model parameters we'd have. Or 70. 23, 22 is 45. 23 is 68, 69. Okay, 69. Sorry. So the ratio though is better. All right, 299 to 69 versus 72 to 324. And every item that we take off, our ratio is getting better because of those covariances. There's lots of covariances we're trying to account for. So we're going to take out the 9 items here. And actually, that's what this is saying. The words at the top there are saying our job is getting easier. Our number of model parameters, the ratio of model parameters to saturated model variance, covariances, and means, the closer that gets to 1-to-1, the better fit is. When it is 1-to-1, we have perfect fit. Right? Before we had, it was close to 5 or 6-to-1. 6 saturated model parameters for every one of our model parameters. We can shrink that down a little bit. So we took out all 9 of the items from this page right here. And now we have 15 items in our analysis. And now we can take a look at fit. Questions? Yeah.
How come both in the homework and like a couple slides back, it says just look at the positive normalized residual?
The positive is,
You know, it was the one
Yeah.
you scribbled on, I think.
no, that was this one.
Positive
Ah.
covariances.
It's because positive covariances are thought to not be by bias of the model, it's by something else you didn't include. Negative is like you're just that the whole model is off, so that's what's causing negativity. It's what's thought in the field. I think if I'm being more precise, I would go with both. If you read, I think if you read a little bit more into Brown's book, maybe not the chapters I assigned, but a little bit further, you'll see that it's preached a little bit more. I don't like Misfit at all, but a lot of times when you fix the ones with positive covariances, the negatives get better too. The flip would happen if you fix the ones with the negatives, you get the positives better. So anyway, that help? Not a good explanation. Bad fit is bad fit, I think, to me. Other people will go a little bit further on it. At some point, it becomes a little bit tautological as to it's negative because of bias, but it's positive because of lacking a factor. But the positive ones have bias in them as well. so I don't know. I think I should probably better be more precise on my slides with this. Did that answer your question, though?
Sure.
That's a no. Follow up?
No?
No. Frustrated? Yeah.
Doesn't seem that important.
No, I would just, if you see Misfit at all, investigate it, positive or negative. I think you can find normalized residuals to be there. Remember, the normalized residuals are like, there are z-tests. It's like a miniature hypothesis test. So you'd expect 5 out of 100 of those to be off just because, chance. But we're looking to tinker around with this as much as we can to get good fit, but then no more. I don't know. That help? No, not really. Yeah, as I've taught this going on and on, I realize some of the things that people say I don't agree with, and that's one of them. Unfortunately, I would actually look at both, and I did. So I should probably not say. I should probably make that distinction. People say this, I say this. Okay, well, let's take a break. I think we're up on it. Another 10 minutes. Cool. Then we'll come back and inspect model fit. Riveting conclusion.